Hi students, today we're talking about compound angle formulas. So it's a bit of an abstract concept to you at first, but soon once you practice it, it will become very practical. So it all comes back to wanting to have exact values for our trig ratios. So instead of relying on our calculator to find trig ratios as a decimal, mathematicians prefer to rely on the special triangles so we can come up with our trig ratios in terms of, root 3 over 2, because something like that is an exact value. Okay, so this is why in university you're able to do work without a calculator, for instance, even when you're doing trigonometry, because we are able to use things like compound angle formulas to come up with exact values for a lot of different angle sizes and radians that we weren't able to before. So I'm just going to kind of give you an overview of what this video will entail, because there is quite a lot going on. So this first page, we are just going to develop one of the 6 compound angle formulas. So there are 6 of them, and I'm just going to show you how to develop one of them, which is cos of A minus B, where A is a given angle and B is a given angle, and you're subtracting them. Okay, so we're going to develop a proof here on this page and come up with a conclusion of what that actually is. Okay, so this is an excellent exercise for anybody going into university that needs practice with this, because you will be doing proofs in university. You will not be required to memorize this proof, but you will be required to understand as I go through it. Okay, the second page, I'll use that example, the compound angle formula I came up with, and show you why it's useful and how we can come up with the exact value of cos of 15 degrees. Okay, and you'll be saying, why are you using degrees, Mrs. Weens? But it's just, I wanted you to be able to use degrees and radians. Okay. Then we'll kind of use cos A minus B to develop sine A plus B. So then we will have kind of developed 2 of the 6. And then here are the 6 that we're coming up with. So you can take the opportunity to pause the video now and copy these down, because this is what we are developing today. All 6 of these is what we're using to solve problems. So on your test and on your exam, you will be given these 6 formulas. You will not have to memorize them, okay? But you obviously have to know how to use them. Okay, then I give a little note here about tan. Then we're going to actually go through with some examples and use these compound angle formulas and see how they're actually useful. So that's what the last few pages are for. Okay, so hopefully you got these 6 down. If you can pause again if you didn't yet, pause and copy those down. And on the front page, we're going to be developing this one. So obviously there's math that could be used to develop all 6 of these, but I'm just going to spend the time developing one of them so you have an idea of how a proof with trigonometry can work. So a compound angle is created by adding or subtracting 2 or more angles. There are special formulas for the trig ratios of compound angles. These formulas allow us to find exact values of trig ratios. So that's the whole point of the note today, is to find these exact values. Now, before I go on, at the top of your page, I just need to remind you of 2 known ratios that we learned in grade 11. Okay, we learned that tan theta is just equal to sine theta divided by cos theta. Okay, and we can prove that using the y and the x's and all that stuff, but that is a known fact in trigonometry. We also learned last year that, sine squared theta plus cos squared theta equals 1. And that is called the Pythagorean identity. Pythagorean, because it just comes from the Pythagorean theorem. So if you want to refresh why those are true, you can come see me or go back to some grade 11 videos. But we assume that this knowledge that you have, okay, when we go through this proof, okay? So let's go ahead and label this diagram. So this here is a right triangle, okay? That's supposed to be showing a right triangle, okay? And so we have this from our initial arm to here, we're going to call that angle A. Okay, and then from our initial arm to here, we're going to call that angle B. So that means that inside here, from here to here, is what we have for A minus B. So that is what we're finding the cos of. This angle is A minus B because it's the blue minus the green is equal to the purple. Now, we're going to label these coordinates. If you can remember, the x value, cos of B, is just equal to the x value, right? Assuming that this is the unit circle. Okay, we're assuming that this is the unit circle. Okay, we have to make that assumption. Okay, so the coordinate here would be whatever x is. Well, that's the same as cos B. So we can say that the x value is cos B and the y value is sine B. Okay, and over here, we can say that this x value is cos A and the y value is sine A. Okay, so those are another way that we can represent those coordinates. Now, if you were to connect these two with a line, you can do that. That creates a line segment that we're going to call C. Okay, so the distance from here to here of this line segment, we're calling C. So what we're going to do to do this proof is we're going to express C in two ways. Okay, so we're going to have two different ways of expressing the length of C, so this point to this point, and then we can set them equal to each other and come up with a result. Okay, so you might be like, well, how does that get us here? Just trust the process, just try to understand each step as I go, and then be able to reflect back on how we got here, okay? You don't have to stress right now that you would have been able to come up with this proof on your own. Your only job as a grade 12 student is to understand this proof as I go through it, okay? So just sit back, relax, and enjoy the show. All right, so the first way we're going to express C is using the cosine law. Okay, so if you see, we have a triangle here to here with C across, okay? So the cosine law says that C squared is equal to the length of this squared, which since this is a unit circle, it's just 1. So 1 squared, plus the length of this, which again is 1, minus 2 times 1 times 1 times the cos of the opposite angle, which is A minus B. Okay, so if we simplify this, we get C squared equals 2, 1 squared plus 1 squared is 2, minus 2 cos of A minus B. Okay, so that's the conclusion we come to there. That's actually, I should have said we're going to express C squared in two different ways. So that's the first way that we're expressing C squared. We just used the cosine law. Okay, now we're going to use the formula. If you remember, these are both actually formulas from grade 10 that we're using to solve this. Now we're going to use the formula for the distance between 2 points. Okay, so if you recall that is distance is equal to the square root, long square root, right, of x2 minus x1 all squared plus y2 minus y1 all squared. Remember that? It came from Pythagorean theorem. We developed that on the Cartesian plane. I think you even had a communication question about why this formula works. Okay, so that means from here to here, C is equal to, we need a long square root here. Okay, x2 is sine A, and x1 is sine B. So sine A minus sine B, oops, that's a B, all squared, plus cos A minus cos B, all squared. Okay, so if we square C, we just get rid of the square root. So we have sine A minus sine B squared plus cos A minus cos B. Oops. Oops. Okay, so at this point, I could put these two equal to each other since they're both in a form of c squared, sorry, all squared, but I'm going to simplify this first because I want to boil it down a bit further. Okay, so c squared equals, now if we FOIL this out, okay, you would have sine A and sine A minus sine B times sine A minus sine B. So that would give you sine squared A minus 2 sine A sine B plus sine squared B, and then plus cos squared A minus 2 cos A cos B plus cos squared B. Okay, so all I did from here to here was FOIL. Okay, I just FOILed it out. Okay, now I'm going to just move stuff around to make it next to other stuff. So I'm going to put sine squared A and cos squared A next to each other. So sine squared A plus cos squared A, and then minus 2 sine A sine B minus 2 cos A cos B plus sine squared B plus cos squared B. So all I did between these two lines was just move stuff around. Now, this is why I went over this at the beginning, because sine squared A plus cos squared A is just equal to 1. And sine squared B plus cos squared B is just equal to 1 from the Pythagorean identity. So that's just equal to 1, and this is just equal to 1. So this whole thing can be simplified into, okay, c squared equals, okay, 1 plus 1 is 2, so 2 minus 2 sine A sine B minus 2 cos A cos B. Okay, so that is where I'm going to leave this. So that is my second representation. So now I'm just going to set this guy equal to this guy and work my magic. Okay, so I'm going to put 1 equal to 2. I'm getting a little squished here, but we actually only need 2 more lines. Okay, so we have 2. I'm going to kind of, how do I squish this here? I wonder what this does. It's on the page. Okay, 2 minus 2 cos A minus B, that's my first equation, is equal to 2 minus 2 sine A sine B minus 2 cos A cos B. So that's sine B. Okay, so a couple of things here. This 2 and this 2 cross each other off because we have a 2 on this side and a 2 on this side, so they're completely gone. Okay, now what else we can do is divide everything by 2. We can divide everything by 2 because everything has a 2 in front of it. So if we divide everything by 2, then all the 2's go away. And then, so what we're left with is cos of A minus B. So, okay, actually we divide everything by minus 2. Sorry, let's just say divide everything by negative 2. Okay, so when you divide everything by negative 2, you're left with just cos of A minus B is equal to sine A sine B plus cos A cos B, which is the final answer, which is what you should have copied down from the previous page. Yay! So cos of A minus B is equal to sine A sine B plus cos A cos B. And that's our final conclusion. Okay, so again, you don't have to have this proof memorized. I just want you to be able to understand each step and the basic concept that we used the cosine law and the distance formula, 2 different representations of the same distance to set them equal to each other and find this result. And so now you're questioning, well, how is it even useful? Like that looks even more complicated. Well, the issue is that we want to be able to come up with exact values. So right now, we only know how to find the exact values when things have 45 degrees, that's from a special triangle. 30 degrees is from a special triangle, and 60 degrees is from a special triangle. Okay, so we know the exact values, the sine, cos, and tan values when 45, 30, or 60 degrees are asked for, or when the related acute angle is 45, 30, or 60 degrees. So that already gives us, 12 angles that we know exact. We also know the ones right on the axes, so pi over 2, pi, 3 pi over 2, and 2 pi, and then any revolutions of those. So that's another 4. So we already know 16 for sure, and that's just within the first 2 pi. That's just within the first period. But now this allows us a whole new world of how many angles we can find the exact value for. So we want the exact value of the cos of 15 degrees. I mean, you can get your calculator out and put cos 15 degrees, you'll get a nice decimal, but it's not exact. We want an exact value. So how this is useful is that we can write, instead of cos of 15 degrees, I can write this as the cos of 45 degrees minus 30 degrees. Now notice these are both angles from our special triangles. So these are both angles for which we know exact values. So because it's this minus this, we know that cos A minus B is sine A, so sine of 45 degrees. Sine B, so sine of 30 degrees. Okay, so in this case, I'm assuming that this is A and this is B, right? A minus B, so I'm using this formula down here. And then plus cos A, so plus cos 45 degrees. Cos B, cos of 30 degrees. So I know each of these exact values, so now I can just sub them in. So using our special triangles, we remember that the sine of 45 degrees is 1 over root 2, and the sine of 30 degrees is just 1 over 2. Okay, the cos of 45 degrees is 1 over root 2, and the cos of 30 degrees is root 3 over 2. Okay, so now we just need to simplify this. So notice that they both have a common denominator of 2 root 2. So we just end up with 1 plus root 3 on the numerator because they already have a common denominator of 2 root 2. So this is the exact value of the cos of 15 degrees. So if you have your calculator in degree mode, you can find the cos of 15 degrees. It's going to be a long decimal number. And then you can also plug this in, 1 plus root 3 divided by 2 root 2. Just make sure you use brackets on your calculator, and it should be the exact same long decimal as you get from this. Okay, but now you don't even have to get your calculator out. You can just do this with special triangles. Okay, so what about sine A plus B? So we're just going to kind of quickly develop one more of these, so I'm not just giving them all to you. Well, recall from cofunction identities that sine theta is equal to cos of pi over 2 minus theta. Okay, that's a cofunction identity. We learned it in the last note. So therefore, the sine of A plus B is equal to the cos of pi over 2 minus A plus B. Okay, see, because theta in this case is A plus B, so we're just subtracting A plus B and making sure that it's in brackets. So this could be rewritten as the cos of pi over 2 minus A. Oops. Cos of pi over 2 minus A minus B, if you take that out. And we can separate these two in brackets like this. And now look, this is just cos of A minus B, where this whole section now is like the A and this whole section is the B. So we know that that from here is just equal to sine pi over 2 minus A sine B plus cos pi over 2 minus A cos B. Okay, so that's just equal to, and this is just, again, equal to cos A, again, from the co-function identities. So this is just cos A sine B plus sine A cos B, which is what we have written here. We just developed this guy right here. Okay, using co-function identities and the fact that we already developed this one. So again, you don't have to have this memorized. It's just showing how mathematics uses itself to kind of prove more interesting things. So this is how math develops. Somebody finds one equality, and then they use that proven equality to prove another equality, and it kind of just keeps going and going and going, and then we're able to use that mathematics today. So the reason why we actually show you how this came up is because who knows, you could be the one who develops something new in the future. So it's important to study proofs and see how things were developed so that mathematics can continue to grow and evolve, and that we have people growing and evolving and finding out new things. So that's kind of exciting. All right, so here you have your 6 formulas. Again, they will be provided for you on a test. I just want to make one note about tan, because tan has this weird thing where sometimes it can be undefined. So if you have pi over 2 or 3 pi over 2 is as part of your tan function, these give a tan that is undefined, so therefore you can't rewrite them. So for instance, if you have tan of pi over 2 plus x, it can't be solved because this gives an undefined value. Okay, so the problem is that sometimes students then just say, oh, I'll just put that as 0. But undefined, and 0 aren't the same thing. Okay, so you have to use the fact that tan theta can be rewritten as sine theta over cos theta. So that means that tan of, sorry, I'm losing my voice, pi over 2 plus x can be rewritten as sine of pi over 2 plus x divided by the cos of pi over 2 plus x, okay? So this is just sine A plus B, and this is cos A plus B, so we can just go back to our addition formulas and fill that in. So this just gives us the sine, sorry, my bad, the sine A plus B, so cos of pi over 2 sine x plus the sine of pi over 2 cos x divided by, now cos A plus B is here, so cos A, so A is pi over 2, so cos pi over 2 cos x plus, oh, sorry, minus sine of pi over 2 sine x. Okay, so the cos of pi over 2, remember pi over 2 is just here around the unit circle, so the coordinates here would be 0, 1. So remember the cos of pi over 2 is just the x value, so that's actually just 0. So this becomes 0, so you get 0 plus, now the sine of pi over 2 is 1, so you just get cos x. And the cos of pi over 2 again is 0, so you just get another 0. Minus sine x. So you get cos x divided by negative sine x, which is just the same as negative cotangent x, because cos over sine is cotangent, okay? Because it's the opposite of sine over cos. So this gets you all the way to just that. So that's pretty exciting. That's fun. I like doing that. All right, so let's go on to some more examples here. Okay, so here we have, so we have to be able to use the addition and the subtraction formulas both ways. So notice we have cos something something plus sine something something. So we can call this A and this B, and notice this is the same value, so this is another A and this is another B. So basically we have cos A cos B plus sine A sine B. So we just go over to our formulas and we say which one has the pattern cos A cos B plus sin A sin B. That's cos A minus B. Okay, so this is just equal to cos A minus B, where A in this case is 7 pi over 12 and B in this case is 5 pi over 12. So this can all be rewritten then as cos 7 pi over 12 minus 5 pi over 12. So that's just the cos then. 7 pi minus 5 pi, that's 2 pi over 12, which is pi over 6. And pi over 6 is from one of our special triangles. So if you remember our special triangle, this is pi over 3, this is pi over 6, this is 2, 1, root 3. So the cos of pi over 6 is just root 3 over 2. So there we go. We're able to solve that exactly. Okay, here's a different one. Simplify sine 2x cos x minus cos 2x sin x. So this is really just saying we have sine A cos B minus cos A sin B, where in this case A is equal to 2x and B is equal to x. So again, what has this pattern? So if you go to your subtraction formulas, then it is sine of A minus B. So this is the same as sine of A minus B. So then this can be rewritten as the sine of 2x minus x. So this is just equivalent to sine x. And that's it. We're done. Okay? All right, so this is a specific type of question. I want you to pay attention to this example because this type of example will come up in your homework and again on your test, I believe. So we want to evaluate sine of A plus B, given that sine A is 3 over 5 and sine B is 5 over 13, given that A and B are both obtuse angles. You might have to add this to your note. I'm not sure if I gave that to you as part of the question, so if you don't have that, make sure you copy it down. So make a little note to yourself. Note that it's sine A that's equal to 3 over 5. It's not that A is equal to 3 over 5. All the time, I just get students like not seeing the sign here. They think it's just A equals 3 over 5. And so they just sub in 3 over 5 and 5 over 13 for that. And that's not what it's saying. It's saying that all of sine A is 3 over 5 and all of sine B is 5 over 13. So let's recall that sine of A plus B is equal to sine A cos B plus cos A sine B. Okay, so the good news is that we already know sine A and we know sine B. So we can sub those things in, but then we still have to do some work to find cos B and cos A. So sine A is just 3 over 5. But we still got to find cos B, wah. And then cos A, we still got to find, and sine B is 5 over 13. So how can we find cos B and cos A? Well, let's recall what it means to be 3 over 5. So if sine A is 3 over 5, that means that it terminates in quadrant 1 or quadrant 2 to have a positive sign value. However, we know that A is an obtuse angle, so that means it has to terminate in quadrant 2, not quadrant 1. So here is our A value. So we can drop down a little perpendicular here. So remember that sine is y over r. So that means that our y value is 3 and our r value is 5. So we just need to find this x value so we can find the cos of A. So using Pythagorean theorem, 5 squared minus 3 squared is equal to 4. So this has to be negative 4, okay, since it's going in the negative direction. And we also know that in this quadrant, cos is negative. So from this, we can conclude that the cos of A is equal to negative 4 over 5. Okay, using the same logic, I encourage you to try on your own to find what the cos of B is. So pause the video right now and try it on your own. Okay, so using the same logic, sine B is positive, but B is obtuse. That means it has to terminate in this quadrant. So this is angle B then. Okay, so we drop down a perpendicular. We know that this is 5 high and this has to be 13 long. So using Pythagorean theorem, you find that this length is negative 12. So cos B then is equal to negative 12 over 13, x over r. Okay, so now you just sub those values in over here and use your fraction knowledge. So 3 over 5 times negative 12 over 13 plus negative 4 over 5 times 5 over 13. And using your amazing fraction skills, because they don't scare you anymore, you can come up with this is minus 56 divided by 65, an exact value. So there you go. All right, here we get into the number 4, and then number 5's a really good nitty-gritty question, okay? Okay, so show that these are all equivalent using compound angle formulas. So really what that means is that we just got to break this up into 1, 2, 3 different equations and just show that they can all be simplified to be the exact same thing. So sine of x minus pi, okay, you just use the a minus b compound angle formula. That's just sine x cos pi minus cos x sine pi. So recall that the cos of pi is negative 1. So you get sine x times negative 1 minus cos x. And the sine of pi is actually just 0. So you're left with just negative sine x. Okay, so now you're just trying to prove that this red one and this green one are also just negative sine x when you reduce them. So sine of x plus pi is equal to, using our compound angle formulas, sine x cos pi plus cos x sine pi. Okay, so remember that the cos of pi is negative 1, so this just gives us minus sine x, and the sine of pi is 0, so that just goes away. So there we go. That one's proven. So now we just do this last one. So cos x plus pi over 2. So that's the compound addition formula of cos of a plus b. That gives us cos x cos pi over 2 minus sine x sine pi over 2. Okay, so pi over 2, the cos of pi over 2 is 0, so this just goes away. And the sine of pi over 2 is positive 1, so we just have sine x times 1, so that just gives us negative sine x. So since they're all equivalent to minus sine x, we have proven our point. All right, one last example, and this kind of really gets into the nitty-gritty of how we use compound angle formulas. And it's your fraction skills are really going to come into play here, okay? If you're strong with fractions, this will help you because you're coming up with these compound angle formulas. So we're trying to find the exact value of the tan of minus 5 pi over 12. So minus 5 pi over 12, let's think about where this guy lives, okay? If we had to draw him on the Cartesian plane, where would he exist? Well, it would be minus 5 pi over 12. That's just under minus a half. So this guy is going to live here. Okay, so going this direction. Okay, so that's the angle negative 5 pi over 12. So that is its own related acute angle. So we do not have an exact value for minus 5 pi over 12. It's not part of any of our special triangles. So we need to use our special triangles, or the ones that we have exact values for, to come up with an addition or a subtraction that adds or subtracts to minus 5 pi over 12. And if we can do that, then we can find the exact value. So we got to think, we know pi over 4, we know pi over 3, sorry, not 13, pi over 3, we know pi over 6, okay, those are the special triangles. And then around the Cartesian plane, we know exact values for pi over 2, pi, 3 pi over 2, and 2 pi. So we know all of the exact values for any of these. So in this case, though, the denominator is 12. So for us to more easily figure out what can we add or subtract together to come up with minus 5 pi over 12, it's easier to rewrite them all with the denominator 12, so we can do that addition and subtraction in our head much more easily. So pi over 4 is 3 pi over 12. Pi over 3 would be 4 pi over 12. Pi over 6 would be 2 pi over 12. Pi over 2 would be 6 pi over 12. Pi would be 12 pi over 12. 3 pi over 2 would be 18 pi over 12. And then 2 pi would be 24 pi over 12. So these are the exact same angles, just written with a common denominator of 12. So from here, we can see, how can we come up with minus 5 pi over 12? Well, minus 5 pi over 12 can be rewritten as minus 3 minus 2. Okay, if we take a minus 3 pi over 12 minus 2 pi over 12, that gets us this minus 5 pi over 12, okay? So we just have to pick 2, and we can either add or subtract to get the right answer. But then we need to put them back into their normal form. So if minus 3 pi over 12 is just minus pi over 4, and minus 2 pi over 12 is just minus pi over 6. Okay, so now we're going to use this knowledge to come up with the compound angle formula for what we want here. Okay. So it's asking us for the tan of negative 5 pi over 12, which can be rewritten as the tan of negative pi over 4 minus pi over 6. Okay, so this is the compound angle formula where we have a tan of A minus B. Okay, so this is the form of tan A minus B. We got to be careful. A is negative pi over 4, and B is just pi over 6. Okay, so we're using that form. B is equal to pi over 6, not negative B over 6, because we're using the form A minus B. So it's minus pi over 6. So B is pi over 6, but A is negative pi over 4. Okay, so now we're going to just sub in our compound angle formula. So it's it's tan A, so tan negative pi over 4, minus tan B, so minus the tan of pi over 6, divided by 1 plus tan A, so tan negative pi over 4, tan B, so tan of pi over 6. So now we just need to sub in what we know. Okay, so if we can remember our special triangles, okay, here is the pi over 4 one. Okay, so 1, 1, root 2, and here is the other one. So this is 2, 1, root 3, but this is pi over 6 is up here. Okay, so pi over 4, the tan of it is just 1, but negative pi over 4 is in this quadrant. Okay, so the tan of negative pi over 4 is actually negative 1. Okay, because negative pi over 4 is in this quadrant. Okay, and then tan of pi over 6, so remember that's opposite over adjacent, will be 1 over root 3. Okay, all over 1 plus, again, the tan of negative pi over 4 is negative 1, and tan of pi over 6 is 1 over root 3. Okay, so this is like the most basic answer here, but we want to actually put this into lowest terms, okay? So if you answer like this, that is correct, but the back of the book probably won't look like this. It's going to have simplified this further. So I'm going to show you guys how to do that. So this can simplify, you get a common denominator on the top and the common denominator on the bottom. So you get minus root 3 over root 3 minus 1 over root 3 on the top, okay? And you get, so the denominator will be root 3 again, so root 3 over root 3, so that's just 1, minus 1 over root 3 on the bottom, okay? So it almost looks like you could just cross off the top and the bottom, but there's one thing that's stopping you, and that's this negative here, okay? So the top and the bottom are not equivalent, okay? So this top can be rewritten as just minus root 3 minus 1 over root 3, okay? Minus root 3, yep. And then this is root 3 minus 1 over root 3. Okay, so go back over here. I'm just trying to use my space. Okay, we can flip and multiply. So you get minus root 3 minus 1 over root 3 times root 3 over root 3 minus 1. Okay, so you can simplify this by crossing these guys off. So you're left with minus root 3 minus 1 all over root 3 minus 1. And that's it. That is your final answer. So that is the tan of your angle that has a size of 5 pi minus 5 pi over 12 radians. That is its tan value as an exact number. So again, if your calculator is in radians, you can go ahead and find the tan of bracket negative 5 pi divided by 12. Write down the long decimal that you get. Now take your calculator and do bracket minus root 3 minus 1 and bracket divided by root 3 minus 1 bracket. And that answer that you get there should be the exact same long decimal that you got for your tan value. So that is the exact value, which has a lot more use and mathematically than just that decimal estimation. So thanks for watching, guys. I hope you learned lots.